This is Physics 1060, Lecture 10. Today we're going to talk about Chapter 11. So the Sun is a star. It's a luminous ball of gas more than 100 times bigger than the Earth. And it kind of looks quiet from our naked eye view, but if we look at it through a telescope, we're going to see a lot of violent activity. Fountains of incandescent gas, twisting magnetic fields. The Sun's core is equally violent, with a furnace of thermonuclear fire converting hydrogen to helium to the tune of energy production equivalent to the detonation of 100 nuclear bombs each second. The force of gravity keeps the Sun in check for now. So with a radius of 100 times and a mass of 300,000 times of the Earth, the Sun has to expend a large amount of energy to withstand its own gravitational desire to collapse. To understand this process requires detailed observations as well as sophisticated calculations involving computer models of the laws of physics. So the Sun's distance from the Earth is 150 million kilometers, or 1 astronomical unit. And it was once measured by triangulation, but now it's done by radar. Once the distance is known, its diameter, which is about 1.4 million kilometers, is found using its angular size. From the Sun's distance and Earth's orbital period, we can use Kepler's modified third law to give us the Sun's mass. And now that we know the mass and radius, the surface gravity of the Sun can be determined. It's about 30 times that of the Earth. So our 180-pound man that we've been talking about would weigh 54,000 pounds on the surface of the Sun. The surface temperature of the Sun is almost 6,000 degrees Kelvin, and it's found from the Sun's color using Wien's law for a black body object. Now then, if we apply the laws of physics as we understand them, we establish the Sun as gaseous throughout with a core temperature of about 15 million degrees Kelvin. From the amount of solar energy that reaches the Earth, which is 4 times 10 to the 26 watts. This energy must be replenished by fusion processes in the core. Now the Sun has plenty of hydrogen for fusion. Its surface spectra shows the Sun is about 71% hydrogen, 27% helium. Now we can start to look at the Sun. We can start with the center out. The center in the core is where we get all the fusion happening. We'll talk a little bit about that. And then we get a radiative zone of that energy coming out. And we get a convective zone where we get the heat from the inner part of the Sun goes up to the coldness of outer space. We have different things on it we need to talk about, like prominence that's coming out here, or sunspots. We have the chromosphere, which is the Sun's lower atmosphere, and the corona, which is the Sun's outer atmosphere. So the low-density upper layers of the Sun, where any photons created there can escape into space, is called the photosphere. This photosphere is going to be the surface that we see with our eyes. Layers below the photosphere are opaque, and photons created there are absorbed and re-emitted by atoms that are located there. So we can't see inside of the Sun. However, we can do calculations that shows that the Sun's temperature and density both increase as the core is approached. The density is similar to that found of water at sea level on the Earth at the Sun's surface, and 100 times that of water at the core of the Sun. Since the core is hotter than the surface, heat will flow outward from the Sun's center. So near the Sun's center, energy is moved outward by photon radiation, a region surrounding the core known as the radiative zone. Photons created in the Sun's interior do not travel very far before being reabsorbed. Energy created in the Sun's center will actually take about 16 million years to eventually diffuse to the surface. Above the radiative zone, energy is more efficiently transported by the rising and sinking of gas, and this is called the convection zone. And convection manifests itself in the photosphere as granulation, or if I look very carefully here, I see granules of material on the surface of the sun. The darker areas are where the cooler gas is falling back into the sun, and the warmer areas is where warm energy is radiating out. You see all the granules here around the sunspots, which we'll talk about soon. Now, since the sun is all a ball of gas, it kind of seems strange to talk about the atmosphere. But the atmosphere is what is going to be above the photosphere, the visible surface of the sun. It's extremely low-density gases that lie above it. The density of the atmosphere decreases steadily with altitude and eventually merges with the near vacuum of space. Immediately above the photosphere, the temperature of the atmosphere decreases, but at higher altitudes, the temperature actually grows hotter, actually reaching temperatures of several million degrees Kelvin. The reason for the increase in temperature is unknown, but there's speculation at this point that it's the sun's magnetic field that's causing this high temperature. The lower part of the atmosphere is referred to as the chromosphere. The chromosphere appears as a thin red zone around the dark disk if we look at a totally eclipsed sun. The red is caused by the strong red emission line of hydrogen spectra, hydrogen alpha it's called. The chromosphere contains millions of thick columns called spicules, each a jet of hot gas. In this picture you can see here all the spicules of jets of gas shooting off the surface of the sun. Now above that is the corona. The temperature in the corona eventually reaches about 1,000,000 degrees Kelvin. Not much energy though, due to its low density. The corona, which here we can see is visible during a total solar eclipse, can be seen to reach outward over several solar radii. The corona is not uniform, it has streamers and holes in it, and those are dictated by the sun's magnetic field. Now, how does the sun work? The structure of the sun depends on a balance between the internal forces, specifically a hydrostatic equilibrium between the force that prevents the sun from collapsing and the force that holds it together. The inward, or the holding force, is its own gravity, and the outward is the internal gas pressure. Without balance, the sun would rapidly change, and we'll see some stars later in the course that are rapidly changing. So pressure in a gas comes from atomic collisions. The amount of pressure is in direct proportion to the speed of the atoms and their density, and is expressed in something called the ideal gas law. Now, given that the sun loses energy as sunshine, an internal energy source must be present to maintain this hydrostatic equilibrium. If the sun, for example, were made of pure coal, the sun would only last a few thousand years. If the sun were not in equilibrium, but creating light energy from gravitational energy, for example, the sun is continually collapsing, the gravitational energy would only let the sun shine for about 10 million years. These and many other chemically based sources of energy are not adequate to account for the sun's several billion year age. This was a big mystery until Einstein came, and the key is the mass-energy relation. So, in 1905, Einstein showed that energy and mass were equivalent through his famous E=mc² equation. 1 gram of mass is the equivalent to the energy of a small nuclear weapon. The trick is finding a process to convert mass into forms of energy. A detailed process for mass conversion in the sun, called nuclear fission, was found. The sun's core temperature is high enough to force positively charged protons close enough together that they touch, and then they will stick together due to the nuclear or the strong force. The net effect is that 4 protons are converted into a helium nucleus, plus other particles and energy, in a 3-step process called the proton-proton chain. So step 1 in the chain. I have 2 hydrogen nuclei, which is just a proton. And they have a high enough temperature, which means they have a high enough speed that if they're coming straight at each other, they'll actually touch. And when that happens, they'll stick together. One of the protons will turn into a neutron. Now it has to get rid of its charge somehow, and so it gives it off in something called a positron. It's an antimatter particle. It's the same mass and everything as an electron, only it has a different charge. And it also gives off another elementary particle called a neutrino. Now the next step in the proton-proton chain is another hydrogen atom comes together. It has the same speed, and the hydrogen and the H2, which is a hydrogen atom that has an extra nucleon, will actually also collide. And when that happens, they stick together due to the strong nuclear force, and it gives off light in the form of a gamma ray. The third step in the proton-proton chain is when the temperature is hot enough, two helium-3 atoms come together, and when they touch, what happens is the two protons and two neutrons stick together and form helium-4. That's the kind of helium that we're most familiar with. It's what we usually blow up party balloons with. But there's two extra protons, and they go off, and they complete the process, and they are free to start the process all over again. This nuclear fusion process in the sun's core creates these neutrinos, I said. Now, neutrinos don't have any electric charge. They have a very small mass, and they escape the sun's interior relatively unaffected. And they shower the Earth. As you're sitting here, about 1 trillion pass through you every second. Now, the neutrino's low reactivity with other forms of matter really requires special detection arrangements. We have detectors buried deep in the ground that prevent any spurious signals produced by things like cosmic rays, which are just very high energy light. Also, any high energy particles like protons or electrons or any other things except for the neutrinos coming from the sun. Essentially, we take very old mines deep in the earth and fill them with water and have very special light detectors that can detect even a single photon of light, as a neutrino might interact with an atom and give off some energy which would come out in the form of light. Now, as we look at our neutrinos, we see that the detected neutrinos are about 3 times less than predicted. So, in science, if we make a prediction and we make a measurement and it doesn't come out the same, then we need to figure out why. Some reasons could be, number one, our model of the solar interior could be wrong. Or it could just be that neutrinos have properties that we really don't understand well now. Now, our current view to explain the measured solar neutrinos is that neutrinos come in 3 different varieties instead of the one that we thought there were. And each have a slightly different mass, and the detectors on Earth cannot detect all 3 varieties at the same time. Now, there's some very important ramifications for this. A solar astronomy observation of neutrinos could lead to a major revision of our understanding of the basic structure of matter. Now, another way we can probe and see what's going on inside the sun is use seismology. Solar seismology is the study of the sun's interior by analyzing the wave motions on the surface or in the atmosphere. And that wave motion can be detected by Doppler shift of the moving material on the surface. The detected wave motion gives temperature and density profiles deep inside the sun, and when we do that, the profiles agree very well with our current models of the happenings inside the surface of the sun. Now, surface waves are but one type of disturbance in the sun's outer layers. There's a wide class of dramatic and phenomena that occur on the sun, and they are caused by the sun's magnetic field. The first is sunspots. And they're just dark-appearing regions. They range in size from a few hundred to a few thousand kilometers across. They last maybe a few days to maybe over a month. Now, in this picture, they look dark, which we might think they look cold. But it's not that they're cold, it's just a contrast. The surface of the sun where the granulation is about 6,000 degrees. The sunspot here is about 4,500 degrees. Now, that's still hot enough that if we had something 4,500 degrees, it would appear white hot to us. But it's not quite as bright, and so when we take a picture, we see a difference in contrast. And the reason it's cooler is that there's stronger magnetic fields inside the sunspots. Now here's a picture of the sun showing several sunspot groups. You can see how big these are. Over on the side here we have a picture of the Earth and how big it is. This sunspot group would fit several Earths inside of it. And the groups tend to go around the sun just like any other object on a surface of a rotating object. So why do we get sunspots? Charged particles tend to spiral along magnetic field lines easier than they drift across them. In other words, as I have some magnetic field lines here, it's very difficult for a charged particle to go through them. However, they can go along them relatively easily. So consequently, magnetic fields at the sun's surface slow the ascent of hot gases from below. So, starved from the heat below, the surface cools because it's in contact with space. Where the magnetic fields breach the surface, they create a dark sunspot. So I have magnetic field lines inside the sun, and where they come out, I get not as much heat flow, and so where it comes out and comes back in, I get sunspots. Now another object that we see on the surface of the sun that's due to magnetic field is something called a prominence. It's a huge glowing gas plume that juts from the lower chromosphere into the corona. You can see these pictures of these prominences as material spirals up and back down onto the surface of the sun. And it stays all together because it's trapped by magnetic field lines. And again, I have some pictures here that show you the size of this explosive material coming off the surface of the sun compared to the size of the Earth. So, the cool prominence gas is confined by its high magnetic field and hot surrounding gas. Gas streams through prominences in varieties of patterns, and they are associated with sunspots. Prominences tend to start and stop on a sunspot. Another object that we see is something called a solar flare. Sunspots are where solar flares occur. They're brief but very bright eruptions of hot gas in the chromosphere. This hot gas brightens over minutes or hours, not enough to affect the sun's total light output, but enough for us to see and shoot out a lot of material from the surface of the sun. There's a strong increase in radio and X-ray emissions during a flare. We have an intense twisting and breakage of magnetic field lines is thought to be the source of flares. In other words, as magnetic field lines come out and back in, sometimes they can get kinked, and as they kink and cross off, the explosion is this flare. Now, some flare eruptions can explosively shoot gas across the solar system, and actually, when there's solar flares, we know that a few days later we're going to have some very good auroral displays on all the planets, including the Earth. So the impact of a solar flare on the Earth is generally, as we see here, the northern lights. Now these solar flares can be very intense, and they can create enough of an effect here on Earth that they can actually cause blackouts. So, while the sun's magnetic field cools sunspots and prominences, it actually heats the chromosphere and corona. Heating is caused by magnetic waves generated in the relatively dense photosphere. The waves move up into the thinning atmospheric gases, they grow in magnitude, and they whip the charged particles back and forth to higher speeds and therefore higher temperatures. The origin of the waves may be from rising bubbles in the convection zone. So, as I have magnetic fields come out, you get this wave, and as that happens, as this wave gets larger and larger in amplitude, it causes the charged particles to move back and forth at higher and higher speeds. Higher speeds means higher temperature. Now we can measure the strength of a magnetic field due to something called the Zeeman effect. Magnetic field lines can split the spectral lines of an atom into 2, 3, or more components by changing the energy levels of the atom's electrons. Essentially, the electrons have something called spin, kind of like the Earth spins on its axis. And depending on whether the spin aligns, is perpendicular, or anti-aligns, I could get, instead of one spectral line where there's a magnetic field, I could get it to divide into 3. By looking at those spectral lines and how far apart they are and how many there are, we can determine the strength of the magnetic field. So the corona's high temperature gives its atoms enough energy to exceed escape velocity of the sun. Those atoms stream off into space and they form the solar wind, which is just a tenuous gas of hydrogen and helium that sweeps across the entire solar system. The amount of material lost from the sun via solar wind is really insignificant. And typical values at the Earth's orbit are a few atoms per cubic centimeter, and they're moving along at a fast rate of 500 kilometers per second. At some point, the solar wind eventually mingles with interstellar space and becomes part of the interstellar gas. Now, sunspot flare and prominence activity change yearly in a pattern called the solar cycle. Over the past 140 years or so, sunspots peak in number about every 11 years. And climate patterns on Earth may also follow solar cycle activity. So the sun undergoes differential rotation, which just means it rotates about 25 days to go around one time at the equator, and about 30 up towards the poles. Now, this rotation causes the sun's magnetic field to wind up, so it increases the solar activity. The magnetic fields essentially start off like the magnetic field from a bar magnet, but as the center of the Earth twists, it starts to twist the magnetic field lines, and as it does, we now get magnetic field lines in coils around the sun. Those coils can kink and break through the surface and cause sunspots. The cycle ends when the field twists too tightly and collapses, and then the process starts over and repeats. And that cycle can vary from anywhere from 6 to 16 years. On average, we said it's about 11 years. Now, if we also look at the polarity of the sunspots, the cycle is really 22 years, because each 11-year cycle, the polarity of sunspots, whether the north pole or the south pole of the field leads or lags, changes each cycle. So leading spots in one hemisphere have the same polarity, while in the other hemisphere they have opposite polarity. Now, we see then that there is some tie to weather, because if you look at Midwestern United States and Canada, they actually experience a 22-year drought cycle. Now, between 1645 and 1715, there was something called the Maunder Minimum. It happened about the same times as what they call the Little Ice Age in Europe and North America. Essentially, there were almost no sunspots during that time. We don't know why. The number of sunspots correlates very high with a change in ocean temperatures. Now, before we leave the sun, I want to review how we use its energy. Depending on what the cloud layer is and what our latitude is, we essentially get about 1 to 3 kilowatts of energy from the sun every square meter on the Earth. So lots of types of solar energy that we use. The first is, of course, just direct heating. You just put maybe some black pipes out, and we'll get hot water that way. We can use solar cells for electricity. Now, plants absorb sunlight, and they turn that into wood, or into fuel. Now, we can eat that, and we call it food, and that energy from the sun then is what keeps our bodies and animals' bodies going. We can burn it like wood and to heat up our homes or to roast marshmallows. We get fossil fuels from plants long ago that have died and have collapsed and have formed oil and coal. The sun also heats our atmosphere and causes it to move around, so wind power is actually a form of solar energy. Hydroelectric power is the sun evaporates water from the oceans, it goes over the land, it cools down and comes down as rain or snow. As it melts again, as it comes back down, we put a dam in its way and we generate power. Or there's another thing called OTEC, which is just the difference between the temperature up at the top of the ocean and the bottom, and using the temperature differential, we can actually generate electricity. The only types of non-solar energy we use would be nuclear energy, geothermal energy, which is stuff from the interior of the Earth, which is heated from the Earth's core and nuclear processes going in there, or tidal energy due to the changing of the tides from the moon.